Today in class, we learned about three of the most important laws in physics. We learned about Newton's laws. Before we go into the demos for tonight, let's review Newton's laws. Starting with number 1. An object at rest will stay at rest. An object in motion will stay in motion with the same speed and in the same direction unless acted upon by an unbalanced force. Number 2. The acceleration of an object as produced by a net force is directly proportional to the magnitude of the net force in the same direction of the net force and inversely proportional to the mass of the object. In other words, the acceleration is equal to the net force divided by the mass of the object. Or, the most common form of Newton's law, the net force is equal to m times a. Number 3. For every action, there is an equal and opposite reaction. Now that we've revisited Newton's laws, if you're still unsure, please go back in your notes from class today. We went over Newton's laws, we went over some examples, we even looked at how Newton's laws applies to everyday life. Pause the video, look over your notes, and then come back and watch. Today, we're going to do a couple of different demonstrations on Newton's laws. We're not going to talk about which law applies to which demonstration, that's your job. As we go through the demos, please write down what law you think applies to each demonstration. Write down a summary of the video, as per usual, and make sure to write down some questions. If you're not sure what law applies to which demonstration, that's okay. We're going to review this tomorrow. Do your best, watch each demo. If safe, do try it at home. Most of the demos that we're going to do today are pretty safe and may actually use some materials that you have at your house. So try it out, practice, see which law applies, and we'll talk about it in class tomorrow. Let's get started. So for this demonstration, we have a piece of paper and we have a textbook. We're going to drop the paper and the book at different times, and then we're going to drop them together. Tell me how Newton's laws applies. Rather than let the paper just fall straight to the floor, we're going to crumple it. Before we do it, tell me what you think. Will the paper and the book fall at the same rate? Will the paper remain to float down? Write down your predictions. What do you think is going to happen? And tell me, why will that happen? What force does not allow the paper, when it's like this, to fall straight down to the floor at the same speed as the book? For this demonstration, you're going to need a plastic cup. This is a plastic wine glass, but a plastic cup is more than fine. Fill it up with a quarter to a little under halfway filled with water, a pie tin, an empty toilet paper roll, and an egg. Now, I'm using a raw egg, but you can use a hard-boiled egg. Remember, science is all about experimentation, so take this experiment, adapt it to however you want to try it out, and let us know in class how it worked. I'm interested, and I'm sure all of your classmates will be too. Take this demo and try it out your own way. Let us know how it goes. So we're going to take our cup and we're going to place our pie tin right on top of it. Make sure that your pie tin is centered right above your cup. Take your toilet paper roll and place that right over where your cup is, in the center of your pie plate. And then take your egg. Place that right on top of your toilet paper roll. Now, what we want to do is somehow get our egg to fall directly into our cup. How do you think we should do this? You see what this looks like. You may know something that looks very similar to this. So predict how you believe we should do this. Before you continue watching, write down your predictions. So when looking at this system here, I can easily remove my tin, remove my toilet paper roll, and drop my egg directly into the watered glass. That's not what we want to do, of course. We don't want to disassemble our whole system. We want to somehow use physics, use Newton's laws, and get our egg to fall directly into our water. Let's see if your predictions, whatever you thought would happen, how we would be successful at this, works. Did you predict that would happen? Did you think that that's what we would do? Obviously, we made quite a mess here, but we were successful. The egg dropped right into the watered cup. So as I'm cleaning up, let's talk a little bit about this. Have you ever seen a magician or one of those magic shows or somebody that's just trying to impress their friends have a full table full of plates and silverware and cups and a tablecloth, and they want to be impressive, they want to show off their skills, and they go over to the table and they pull the tablecloth out really quick, and all the plates and napkins and everything that's on the table stays. How do they do that? First of all, have you ever seen that? I've seen it, I've tried it, and believe me, it didn't work for me. I made a mess, and I broke some dishes, and it wasn't good, and my mom yelled at me. I was much younger, but I wasn't successful at it. Have you ever tried it? And have you ever seen it? I'm curious. I have seen it, and when they do it in magic shows, people are always so impressed, and it's, wow, I can't believe that he did that or she did that. Well, how does that compare to our egg experiment here? What's similar about it? What's different? If you use this with a tablecloth and I had cups on my tablecloth, does it matter what kind of tablecloth I'm using? Does it matter the friction of the tablecloth, the friction between my tablecloth and the plates and the cups that are on it? Does it matter? Does a smooth tablecloth allow the plates to stay on? Does a tablecloth with lots of ridges, will that pull the plates right off? How does that compare? How does this compare to Newton's laws? Here I have two toy cars. I did measure these cars and they are equal in mass, so mass is not a variable in this demonstration. The mass of the cars should not affect how fast or slow these cars are traveling when I push them. How is the acceleration of the cars related to the distance they travel? If I'm pushing the green car with a greater force, what does this mean for the distance the green car will travel? How does this compare to the distance of the white car? If I were to push these two cars with an equal force, knowing that their mass is equal as well, tell me something about the acceleration of the cars. The green car obviously traveled a greater distance than the white car. Is this what you predicted? How does this relate to Newton's laws? Which of Newton's laws is evident in this demonstration? Remember how I told you physics is everywhere? I told you that whatever you're doing, you go outside, you wake up, you turn on the remote for your television, you're using physics. Well, check out this demonstration. See how easy it is to show physics in your home. So I'm going to stand here and I'm just pushing on this column. Now this column holds up the second floor of the house. As I'm pushing on this column, what am I doing? What am I exerting on this column? I'm not strong enough to push the column all the way through. We know that it's standing straight, the house didn't fall, so I'm not doing anything really significant to this column. But I am pushing with a really, really strong force on here. Now, I'm pushing on this column. What is the column doing back to me? Keep Newton's laws in mind. Take this image right here and create a free body diagram of this image. Show me, show the column, and show the different forces acting between us. Also, tell me about Newton's laws. Which of Newton's laws am I representing? What's really going on here?